everyone. Welcome to this month's BSA COTE event. This presentation is on a really timely and hot topic in our industry. Before we get to that, and introduce our co-chairs, I'm Patrick Murphy. I'm the Director of Sustainable Design with Vanderwell Engineers, and I am co-chairs of the Committee on the Environment with Michael Grant, who has a couple of committee business items to alert everyone to.
All right, good evening. Thank you for joining us. This is Michael Grant from BSA COTE. Two things. One is looking ahead to next month. Next month, we're going to have Opal Architecture, Research and Design from Maine, and that's a smaller mission-driven firm who has an innovative practice that does various architectural typologies, but also has done some really interesting things in terms of non-traditional practice and some things that they've gotten involved with product design and fabrication. And so for those of you who are interested in learning more about sustainable firms and different practice models for slightly smaller firms rather than larger firms, this will be a good session, I believe. We also wanted to mention, and we'll continue to mention, that this June, we are going to be changing co-chairs. So 3 years has gone by quickly for me. And we also had Alejandra Menchaca and then Patrick Murphy joined. So we are looking for the new co-chairs for BSA Committee on the Environment. And we ask you to consider whether that might be a role that you'd be interested in. If so, we would like you to write a brief statement of interest and a brief bio and send that to Susan Green at the BSA, and she will post it for folks' review. You'll find her email in the chat at the top of the chat. It's sgreen@architects.org. And the way the committee has done this, the BSA co-chair is not one of the elected positions in the government of the Boston Society of Architects. The committee has traditionally chosen its new co-chairs through election, through a vote of the committee. So what we'll do is folks who are interested will send their blurb, we'll post it, and then in the June session, we'll take a poll and we'll elect the new co-chairs by vote of the committee. And the committee is whoever is in attendance for the June session. So we hope we'll have some great folks. We've heard some good interest already. And that's, thank you very much.
And if you have any questions on what being a co-chair means, you can certainly ask me or Michael. You'll put our emails in the chat, right, Michael?
Yes, I will. And I'll talk to Alejandra. Maybe next time we can add her as well. I want to get her okay for that. But Alejandra would also be a good resource for that
great.
Kind of information as well. We're going to post the blurbs that I submitted, that Ali submitted, and that Patrick submitted as well. So you'll have a sort of reference point for where you might want to start. Thank you very much.
Thank you, Michael. All right, so now it is my pleasure to introduce our presenters this evening on a very relevant topic. So, my perspective as an engineer, as an energy analyst, I've focused on operational carbon emissions, while the architecture community, especially in the last couple of years, has really started to focus on the embodied carbon and the life cycle of the materials that are used. And also, we're collectively confronting an existing building challenge that we can design new construction and major renovations, but that's really only a fraction of the building stock and the projects that are out there. So what are we going to do with our existing building stock? Treating it as an asset that we've already invested in that carbon and the life cycle of all the materials for that building, but how do we improve the performance of those buildings such that we're able to make these buildings achieve the net zero goals that, say, Boston has, the net zero emission goals, things like that. And so our presenters tonight really, they have a case study of showing their way of thinking about balancing all of that, especially, the intersections of operational and embodied carbon, existing building challenges, ways to think about ways to improve those existing buildings. So with that, let me introduce our two presenters. So first is Lori Ferris. She is the Director of Sustainability and Climate Action from Goody Clancy. And we also have Elaine Hoffman, an associate from Goody Clancy, who will be guiding us through the presentation today. Before they get going, and you're welcome to start sharing your screen, I want to give everyone the heads up that this, if they'd like a certificate for attending this, and I believe this is eligible for continuing education credit, I will put a link in the chat. So please click that link and fill out the form to get your credit. With that, let me hand it over to Lori and Elaine. Thank you.
Great, thanks, Patrick. That was a nice introduction. I'm really happy to be here tonight speaking to a group of like-minded peers on this topic. So as Patrick mentioned, we'll be describing, talking to you about quantifying total carbon for smart building reuse. All right, you already met us, that's great. I'll just add that I'm also, as of this year, a member of the National COTE Advisory Group, so it's nice to make the cross-COTE connections here. So our agenda for tonight is pretty simple. We're going to start by doing a general overview about life cycle assessment for existing and historic buildings. I think the topic of life cycle assessment, we're all becoming a little bit more literate in this. There's been a lot of discussion, but there's still a bit of a gap when talking about how to apply LCA to historic and existing building projects. We'll then do a brief example looking at how to use life cycle assessment to evaluate independent retrofit decisions and really look at how to reuse existing buildings. And we'll take it up a scale to look at life cycle assessment to quantify total impacts of building reuse. And then I'll do a brief little intro preview into a tool that we're working on developing. All right, so I think this crowd is quite familiar with these statistics, but we're really working on a deadline here. We know that in order to really cap global warming at 1.5 degrees Celsius and avoid the worst impacts of climate change, we need to reduce our global emissions by 65% by the year 2030. And that is just, screaming towards us day by day. And in order to do this, we need to make reductions we need to find strategies that make reductions quickly. We don't have time to wait for the full life cycle of a building to see carbon benefits. So we need to look for strategies that make meaningful reductions in the very near term. At the same time, we're faced with this challenge of just astronomical growth in square footage. Between now and the year 2060, we're projected to double our built square footage. That's roughly building a new New York City every month around the world. And that's, to look at trying to reduce carbon emissions while still managing this growth is a huge challenge. But existing buildings are really an asset here. We know that by reusing and retrofitting an existing building instead of building new, we reduce that upfront carbon emissions, the embodied carbon emissions, by up to 70 to 85%. So it really challenges us, I think, to think more carefully about how we can reuse the buildings we already have before we build new. And it's not just about carbon, that's what we're going to be really focusing on today, but we know that the impacts of building materials expand into all different types of environmental and human health impacts. Globally, raw material extraction is responsible for 90% of biodiversity loss. We know there are tremendous human health impacts associated with processes like manufacturing of bricks. So there really impacts both at the site of the building and throughout the entire supply chain that we need to be thinking about. Back to carbon, buildings are responsible for 40% of emissions globally. 28% of that roughly is from building operations, while 11% are from the materials going into buildings. And so when we reuse an existing building, we have the opportunity to drive down both of these wedges, both by improving efficiency, reducing the operational emissions, and by avoiding the creation of new materials and new construction, driving down that 11% of embodied emissions. And thinking back to that time value of carbon, I think it's helpful to plot these emissions over time. Looking at operational emissions, we can see, at the beginning of a building's life, there are 0 operational emissions, and every year as the building runs, it uses a certain amount of electricity, and that's responsible for a fairly steady rate of carbon dioxide emissions over time. And every time we intervene in a building, we have the opportunity to reduce that slope. So that's what we're looking to do every time we retrofit or renovate a building, is to push down that slope as much as possible, resulting in a total operational savings over time. With embodied emissions, on the other hand, we start with a large upfront chunk of emissions, but then emissions really happen only at those points of renewal, and it's fairly steady the rest of the time. And I want to point out that unlike with new construction, we're not concerned about the embodied carbon of the material that already exists. That's a sunk cost. What we care about here and what we're trying to reduce are the embodied emissions associated with materials that we add to the building every time we renew it. And ultimately, it's about the total carbon. It's about adding those two together and understanding the cumulative total carbon over time, and looking for the best ways to reduce it as quickly as possible. One resource that I find really helpful here is the recent World Green Building Council report, Bringing Embodied Carbon Up Front. I really love this chart that shows the relative impacts of different carbon reduction strategies in the built environment. And of course, the most impactful thing we can do is to build nothing, which is associated with 0 carbon emissions. But really right up there on that curve is to build less and make better use of what we already have. And while we think of high performance new construction as a really impactful strategy, in fact, it's quite low down the tail. And so it kind of puts the whole thing into perspective. And I think most of you are probably familiar with life cycle assessment, which is the tool that we use to quantify those life cycle impacts. And it's a technique that's actually quite simple. It's used across many industries, but it really just quantifies the environmental impacts associated with all stages of a product or assembly from cradle to grave. And for buildings, we have a number of tools, software tools and data sources available to support this process. The 2 case studies that we'll show you today were both performed in Tally, which is a plugin to Revit, which makes it very convenient for us because in our practice, we use Revit to document all of our projects. So that works fairly seamlessly into our design process. But these other tools are all really valuable, as well as the data sources, which are helpful for doing quick LCA studies when you don't need to build a whole model. And then I just want to end this introduction by pointing out that LCA is a tool like energy modeling or like any other analysis tool, and you have to know what questions you're asking in order to get meaningful data out of it. And when we're talking about life cycle assessment for existing buildings, the range of questions you can ask varies hugely. It can be very detailed. We can ask, should I use insulation A or insulation B to reduce my carbon footprint, all the way up to the very large scale, how much carbon can I save by reusing this building over the next 10 years? And so we'll kind of try to illustrate some of this range of questions that LCA can help us to answer. So I'm going to pass it off to Elaine for this first case study.
All right, thanks, Lori. So the first case we're going to walk through today is this deep energy retrofit feasibility study, where we're evaluating, as Lori described, really total carbon impacts and carbon trade-offs at the very beginning of a project. Next slide. So Goody Clancy was hired to perform what was actually called a deep energy retrofit feasibility study for those 2 1960s residence halls that were shown on the last slide. And the design team was comprised of Goody Clancy, Van Zelm engineers, and Thornton Tomasetti. Next slide. And so typically when we think about the best way to sort of reuse the built environment, we commonly think of deep energy retrofits, which tend to be defined sort of solely focused around operational energy. And I'll just read these 2 definitions here. So Rocky Mountain Institute defines them as whole building analysis and construction process that achieves much larger energy cost savings, sometimes more than a 50% reduction, whereas the New Buildings Institute defines it as a project that achieves at least 30% energy savings in a building. Next slide. But with those definitions, really aren't doing or recognizing the other carbon impacts. And so what we're trying to do through the course of this study is to define what a smart energy retrofit would be, which what we're terming it as one that saves more carbon than it spends by the year 2030. And that's sort of the most important aspect of this definition, but it also accounts for embodied, operational, and end-of-life carbon emissions, strategically improves building energy performance through minimal addition of new material, and positions the building within the bigger picture of the greening of the grid and utility upgrades to maximize the carbon reductions over time. So for this study, we began by identifying project goals, established evaluation criteria, created an extensive list of potential scope items, analyzed these scope items relative to the established criteria, proposed phasing and bundling of the scope items, and also drew some conclusions. And our primary objective here was to establish a method for designing a smart energy retrofit. We also wanted to understand which interventions have the best financial and carbon return on investment, draw conclusions about energy retrofit approaches that are broadly applicable, and create a project that supports the campus's carbon neutrality goals within real world constraints. So for renovation projects, there are clearly many factors that drive the project scope. And so over the course of this study, we were evaluating scope items against all of these criteria, but for the purposes of this presentation, we're going to really be focusing solely on operational carbon and embodied carbon impacts. Next. So, sorry. I was thinking I think it's a higher number of what we looked at in total, but we evaluate over the course of this project over 50 energy conservation measures, and I think over 125 scope items, and those included scope items within end-of-life replacements, envelope upgrades, zone level HVAC upgrades, and also primary energy source upgrades. You can go to the next one. And so the starting point of this study was to understand what the baseline operating conditions of the building were. So through both exterior system survey, comparing existing drawings, using infrared thermography, we mapped out the existing insulation across the whole facade to understand, among other existing conditions, really what the actual R value is. Because as you can see here, because the dark blue is indicating areas on the building that actually have no insulation. So part of our challenge here was to understand both sort of discrete conditions and how all those came together to impact the overall performance. And this formed the basis of, our first round of analysis. So you can go to the next slide. Thank you. So the first step that we took was to conduct thermal analysis, and Goody Clancy conducted that both for the existing conditions and potential interventions to mitigate some of the more severe thermal bridges in the buildings. And then that fed into the whole building energy modeling, both to capture the existing conditions and to analyze the energy conservation measures that we were looking at. And Thornton Tomasetti conducted the whole building energy modeling. So here's an example from the thermal modeling. One of the most significant thermal bridges in the project are these projecting bays. And as you can see in the photo, they were really very prevalent across the whole facade. And so we looked at several different intervention options, including adding insulation at the interior, as well as over insulating. And this bay overclad option that infills the vertical gap between the bays had by far the greatest improvement to the R value at this location. And this is showing as an output from the whole building energy modeling, the 10 most significant operational carbon savings. So the two most significant ones are the two different options for window replacements. And besides that, all of the other most significant improvements were building system or energy source improvements. And actually the only envelope upgrade in the top 10 list is that bay overclad intervention that we were just looking at, shown in blue. And so then moving into the second round of analysis, this is where Thornton Tomasetti used parametric energy modeling to study 240 combinations of ECMs and really assess their interrelationships. And Goody Clancy at the same time started conducting the life cycle assessment. So we'll take a look at that. And so this is an output from that second round of energy modeling. And we wanted to show it because it really emphasizes how important it is to not be looking at scope items just in isolation, because as you can see here, and this is showing, in columns, you can see different HVAC upgrades, and in the rows, you're seeing different envelope upgrades. But if you're doing, just a basic HVAC upgrade, then increasing the insulation might have a relatively significant impact of, 8%, as it's showing here in the first row. But if you're doing, a really significant HVAC upgrade, then it might not have any energy improvement. In this case, we're looking at, it's showing a 0% improvement in terms of cost impact. And if you go to the next slide, this is showing, similar information, but in this case, in terms of relative EUI impact in terms of cost. But that spread is significant, and it represents one of the more important challenges when you're trying to do this evaluation at the beginning of a project, and there are like an almost infinite number of bundles. It is important, to try and create them, because just looking at these things individually really isn't going to give an accurate picture. So next slide. And this chart is showing sort of similar interrelationships, but instead of HVAC zone level upgrades and envelope, it's looking at zone level upgrades combined with different energy source upgrades. So again, you're seeing a really significant spread, like almost double. And so we can go to the next slide. And so then shifting from operational to embodied carbon, these are the embodied impacts of several of the selected envelope scope items. And I think what's important to note here is that there's just really a very wide range of different impacts, particularly because some of these are showing sort of the same R value improvement, but vastly different GWP impacts. So, and of course, there are a few at the bottom here that are immediately positive. So you obviously want something with as low of an impact as possible. So next slide. So this is one attempt to combine the operational carbon impact with the embodied carbon impact. And the way that we're doing that here is in terms of carbon payback period, shown here in years for the time that it takes for the operational savings to surpass the upfront impact. So, you know, similar to the last slide, the best ones, of course, are the carbon saving materials that are also giving you immediate savings operationally. So those, you know, are showing up in the green carbon positive zone, ironically, below the axis. And another way to look at operational and embodied carbon together, and maybe perhaps a more holistic way than just looking at the payback period, is to chart the carbon impact trajectories over time. So this is showing 4 different scope scenarios from the project, looking at the upfront embodied impacts of the envelope scope items. Bear in mind that the only embodied impacts that we calculated on this project were envelope. We didn't include HVAC in that, but nonetheless, these sort of 4 scenarios, while they could all be technically considered deep energy retrofits, they're vastly different in terms of both their immediate carbon impact and their carbon impact in the year 2030. And if you go to the next slide, another layer on top of that is that it's important to design with the awareness of future utility changes. In this case, you know, there's a planned geo-exchange system for the campus that's anticipated to come in online within a few years. And so it's important when you're doing the systems upgrades to be taking that into account so you can get the immediate savings sort of automatically when that happens. And it would be a mistake because you would have the line, otherwise if you didn't take that into account, those lines would continue in their other trajectory, creating sort of a larger gap between, you know, in this case, what we're seeing is the green line with really significant carbon savings by the year 2030 versus, you know, what we saw on the previous slide where it was sort of lingering right around 0. So we can go to the next one. So what did we take away from all of this? I mean, I think there were some lessons learned that could generally be applied. And one is that maintaining the building envelope really does play a very significant role in reducing energy consumption. You know, consistently in what we were looking at, we saw that it was more significant than the upgrades to the building envelope that you might have anticipated having more dramatic savings. And also that the carbon reduction potential is limited at the building scale. And building retrofits must be designed for compatibility with greening energy sources to maximize carbon savings, sort of reiterating what we were looking at on the last slide. And here are just some strategies, you know, based on all of the data that we were looking at to make all retrofits smarter. The first one being, you know, one approach could be to establish maximum carbon return on investment as a project criterion, or to establish, you know, a moment in time for which you're trying to optimize carbon impact. Measure total carbon, optimize carbon payback for envelope, end of life replacement or refurbishment measures, evaluate retrofit interventions at envelope weak points for effective reductions in energy use. And as always, you know, look for opportunities to store carbon through new materials, because that's the best way to get, you know, immediate carbon savings.
Great, thanks, Elaine. So now that Elaine's taken us through this detailed case study, I'm going to bring us back up a few levels to the whole building scale, look at quantifying the benefits of whole building reuse. And I'm going to do this through a case study through the renovation of what was formerly the Boston University Hillel Center and is now their admission center. It's this really lovely international style building from 1953, which we renovated with a great team of engineers and consultants. And this was a fairly intensive renovation. It was a completely new interior, comprehensive renovation of the interior with some additions as well. So you can see in this little axon, there's an addition to the north. This building sits along the Esplanade, sort of along Storrow Drive. So creating more transparency and connection to that river view on the north, as well as improved circulation. There was a rooftop addition to house new mechanical equipment and a new entry canopy to welcome visitors and students from the main campus. And as part of all of this work, we performed a number of upgrades to the envelope, which included all of that new glazing, and the new facade and the existing windows were replaced with double glazing and thermally broken frames. We did insulate the interior face of all of those exterior walls, and as well as insulating the roof. And all the systems were new, which included VRF units and high efficiency condensing boilers. And through all of this work, we were able to maintain 86% of structure and enclosure. And we note structure and enclosure specifically because we know that those are the two components, systems of the building, which contain the most embodied carbon. And with all of that work, we were able to make really substantial reductions in the operational energy use of the building. Compared to the CVEX baseline, we're seeing a 70% reduction. And this was exciting for us. It was a few years, or very, near the beginning of our Architecture 2030 commitment journey. And this was one of our early projects which met the targets. And it was a good precedent to show that existing buildings really can meet those targets just as well as new construction can. And a number of years after the project was completed, once we had sort of started our practice of life cycle assessment within the firm, we went back to a few existing old projects, completed projects, to run a life cycle assessment to sort of try and benchmark and understand what the carbon footprint of our work looks like. So what you see here are the results from Tally, from that Revit plugin life cycle assessment tool. And you can see the impact across a number of different impact categories noted on the bottom. And circled in red is the global warming potential, which is that carbon footprint. And you can see here the carbon footprint of all of the materials that we added to this building through the course of the renovation are approximately 400,000 kilograms of carbon dioxide equivalent. And more so, we can break that down. We can understand which parts of the renovation are contributing, which materials are contributing the most to that carbon footprint. And even in a renovation, we can see that structure plays a huge role here. 40% of the total impact is from structure. And a lot of this has to do with the fact that where there were multiple added pieces to the building, as well as a pretty significant amount of site work and retaining walls, new concrete around the substructure of the building. And then after that, it's really windows and interior partitions. And we find this in most of our renovation projects, which makes sense that when you're completely renovating the interior of the building, those interior partitions have a really large footprint. And insulation, also seen here, is fairly significant. And once we know what the biggest contributors are to the global warming potential, we can then ask ourselves, how can we reduce them? How can we take those most important materials and try and drive down their carbon footprint through material substitutions? So this exercise just examined, what happens if we trade out traditional drywall for a low carbon drywall like USG EcoSmart. And we can see that single material substitution results in a total reduction to the product of 4% of its carbon footprint. The largest reduction we saw from a single material substitution was through insulation. So the project used mineral wool, which is a pretty good insulation, but it doesn't store carbon. So we said, what if we use cellulose instead of mineral wool, maintaining the same R value? And that substitution would have resulted in a reduction of 11% of the entire building, the entire project's global warming potential through that material substitution. So this was really valuable to us in understanding the kinds of materials decisions that we should be making in the future as we retrofit buildings and as we build new. Again, it's all about total carbon. So we want to add those two things together and look at them together, both operational and embodied. So on this project, we can look at our renovation compared to a comparable new building. And because with the renovation, we were able to reduce our operational energy by 70% below CBEX. And from an embodied carbon standpoint, we saw a 70% reduction compared to a comparable new building. With those cumulatively, by the year 2030, we've avoided total carbon emissions equivalent to 2.3 million miles driven by a passenger vehicle. So, it really adds up. We can also look at how those carbon emissions occur, how they accumulate over time. And starting with the unrenovated building, we can see here, obviously at year 0, if we don't do anything to the building, there are no embodied carbon emissions, and it operates as it always has, with a slope representing its operational efficiency. Then layering on the renovated building in orange, you see there's a small amount of embodied carbon at year 0 at the point of renovation, but that slope is really dramatically reduced, and that represents that gain in efficiency and operations. And with this renovation project, the upfront investment from the materials pays back with that increased efficiency in just 4 years. We always get the question, wouldn't it be better to just tear it down and build a high performance new building, a net zero new building? So we can look at that also. And when we look at a new building of the same size and sort of standard current construction practices, we can see there's a much larger embodied carbon footprint up front. And I've given it an extra 15% reduction in operational energy as a little bonus. And even with that boost in operational performance, it still emits more carbon over the first 30 years of life compared to the renovated building. But that's not really the whole story, because we know that the grid is greening. And Elaine mentioned this, sort of looking at our renovations in tandem with utilities. This is really important when looking at whole buildings also. So here in this chart, I've taken into account the fact that in Massachusetts, we've committed to an 80% reduction in emissions from our grid by the year 2050. So you can see that particularly if we electrify existing buildings and new construction, those slopes will go to 0 as emissions from the grid grow to 0. So in this case, even more so, you can see that the renovated building and the replacement building lines never cross, meaning that basically, for the rest of its life, the renovation results in a lower carbon footprint than the replacement building, no matter how efficient the replacement building is. All right, so that's the end of the case studies, and I just want to leave you with a preview of a tool which I have been developing with Larry Strain of Siegel and Strain Architects and Aaron McDade of Architecture 2030, and this tool is really to help people answer that question: how much carbon do I save by reusing an existing building? How can we, can we easily put a number to the old saying, the greenest building is the one that's already built? So the tool it evaluates total carbon emissions of existing building reuse compared to new construction. And it's really an early stage tool. It's targeted at planners, at preservation officials, building owners or developers who want to understand, I have an existing building, what's the best thing to do with it? How much efficiency do I need to gain? Or what decisions do I need to make to understand the total carbon potential of that existing building compared to a replacement building? And so it looks at 3 scenarios: an existing building baseline, a retrofit, and a replacement, similar to the charts I just showed. And it quantifies embodied carbon, operational carbon, and avoided carbon impacts. And this is a quick peek at what it looks like, although it might look different by the time anyone sees it again. It's an Excel tool with drop-down menus. There are a number of options that you can select for those renovation and upgrade choices that are made. There are a lot of ways to reuse the building. There are 4 options for new construction. You can select to try and represent closely the building that you would put back. There are options for operational efficiencies. You can sort of set the target EUI you're trying to achieve for both the existing building and the new building. And there are embodied carbon modifiers to try and customize this as much as possible to account for things like poor soils, blast resistance criteria, that sort of thing. So just for this presentation, I ran that BU case study through the tool to show you how it works and also to check the tool's data. It came out pretty well, which was reassuring. So you start by entering the basic building information, the location, the climate zone, what its use type and its size, as well as the timeline you're looking at. And that's really important because this tool is to look at near-term impacts to meet carbon neutrality targets. So we're really looking for 10, 15, 20-year life here. So we've entered the existing building information about the upgrades, as well as the extent of renovation on the interior, and set a target for performance. We can then approximate what the new building would be. In this case, I'm saying the new building would be the same size. It's going to be a typical concrete or steel construction. And I'm going to say that it'll have an 80% reduction in energy use below code. And I have not included any embodied emissions modifiers. And so what you get is this chart, which shows you the carbon of doing nothing to the existing building, retrofitting the existing building, and replacing the building. You can see sort of what the contributions are from embodied and operational emissions, as well as the avoided emissions from each of these decisions. It also summarizes the total carbon, so you can kind of quickly get a high level relative quantification of to do nothing to a building, to retrofit it, or to replace it. And it's interesting to see how this changes. It really does change a lot based on things like your grid. For example, if you are in a climate with a very dirty grid, then replacing an existing building with a net zero new building may actually make sense. Whereas if you have a clean grid, then the performance of the new building makes less of an impact. So anyway, we think it's a pretty nice way to quickly see that total carbon story. And I'll just leave you with a few resources. If you're interested in learning more about this intersection of carbon and existing and historic buildings, obviously the Carbon Leadership Forum is an amazing resource for all things related to embodied carbon. The Boston Society of Architecture's Embodied Carbon 101 series, which is online, is really great. And the Climate Heritage Network and ZNCC are both resources and groups to get involved with if you're interested in existing and historic buildings and climate action. Thanks. All right. I'm going to stop sharing now and open it for questions.
Great, thank you. That was a fantastic presentation, Lori and Elaine. I want to remind everyone in the audience, if you missed this before, if you are looking for a certificate for continuing education credit, there's a link in the chat. I'll copy it there again in case you don't see it. But we have our first question or kind of conversation from Connor in the chat. So oftentimes decisions are made early in a project's life to demolish an existing building due to concerns beyond carbon reduction, like accessibility and oh, I lost it.
Low floor to floor height.
Yep.
I could add to the list.
yeah, lots of reasons. So how do you factor in all of those, or how do you look at that?
Yeah, that's a good question. And Connor, specifically asks, how far have you been able to go to reuse the building for the benefits of total carbon, with other factors at play? And I've never saved a building solely using a carbon argument. So I think that it is a point of discussion as carbon mitigation policies are implemented and become more stringent. I think the conversation changes a little bit, particularly when there's an economic, a financial penalty or benefit associated with that carbon number. There are challenges to reusing buildings. I feel pretty strongly that most buildings can be reused, and part of this is a conversation about finding the right use for a building, which is not always possible. I don't know, it says this is a conversation. So Connor, I don't know if people can unmute and participate.
Hi, yeah, this is, sorry, this is Connor. Thank you for answering. I realized that it was sort of a broad, lots of answers to be, lots of paths to go down with it, but it's just young in the field, and the project we're working on now is a old 1960s school that only a little bit was able to be saved, but it's great to be able to do that. But it was determined pretty early on that there were limiting factors that just made it not practical. So it's just a question that's been lingering in my head for a while is, how far can we go? to save an existing building when so many things seem to be stacked against it for its potential reuse. So I thought this would be a great place to first air that question.
Yeah.
But anyways, thank you for your answer. It makes sense that there's always going to be practical concerns, but making this more of a priority, I guess, at the front end, continuing to sort of beat the drum, I guess.
Yeah, absolutely. And I think particularly with buildings of that era, I know part of the argument against them is really just people don't like them. So I think the practicality gets a little bit blended in with the fact that they're just unpopular. But the fact is that they are, when we talk about historic versus existing buildings, those buildings are sort of moving towards that historic, categorization as they get older. So it's not just the environmental argument, there are social arguments and, heritage arguments that can come into play as well, I think, for buildings of that era and older.
Yeah, absolutely.
And I think, that's a really interesting way of looking at it, like from a maximalist position of saving a building versus not. But I think, Lori and Elaine, your first case study where you really zeroed in on specific parts of an existing building, that regardless of what you might be doing the rest of the building, like looking at it both in like a micro scale and a macro scale, I thought was really interesting way to think about it, because I know from all the life cycle cost analyses I've done, insulation doesn't always necessarily make sense. And when you layer into it the embodied carbon and the life cycle of the insulation, it produces some interesting results and kind of focuses the team on really what matters and what doesn't. So thank you for that. So, and by all means, everyone in the audience, you can either submit questions to the chat or you can just come off of mute and speak up. But I want to speak to or ask Lori and Elaine to speak to, in the case studies where you were looking at the existing building energy use versus opportunities to improve upon the energy use. These were presumably buildings where there was already some major intervention in the project, in the building occupancy going on. Is that fair to say? Like as a major renovation or?
Yeah, I mean, I think in the case of my case study, it wasn't any sort of change to the use of the building. It was just really mainly driven by the need for significant deferred maintenance.
That's a good point.
but I mean, that's again just like a classic like moment of intervention that creates this opportunity for all these other upgrades.
Yeah, I think that's an important distinction, because the case study I presented was obviously a complete renovation project, and an improvement in efficiency was just sort of inherent. Like that was going to result basically no matter what we did, and we made good decisions that optimized that. But it was at a point of major intervention, as opposed to the other case study that Elaine presented, which really was about picking the right move so that you could do a really minor project and still come out of it with the best possible steps towards carbon neutrality. Because it wasn't, it was going to happen over a summer. The building, that was the only time the building was empty. It was 3 months, small budget. What were the targeted impacts that you could make?
Yeah, I think that's an important point that I think we all as designers, as practitioners, can apply the lessons from your presentation to nearly every type of project, scale of project that we do. That there are lessons here all the way from those smaller projects or limited scope projects up to whole building interventions. And I think especially as we focus on existing buildings, perhaps once there's teeth put into Bordeaux and to New York Local Law 97 and places like that, where buildings have to make these interventions or pay penalties for their energy performance, that'll kind of force these discussions even further. There's a question in the chat. When will the carbon calculator that Lori presented be available?
Good question. We'll have a beta version available in the next month or two. So if you're interested in playing around with it, I'm happy to share that version. Probably won't be distributed to the entire public, but we can share it with people who want to try using it. And hopefully later this year, it will be more broadly available. We're in a data collection phase right now because I think anyone who has a lot of experience in this area knows that there's a dearth of data, that especially around existing and historic building projects, there's almost no data about life cycle impacts. So we're trying to make sure that we're trying to validate essentially the assumptions in the tool to make sure they reflect real projects.
Lori, who's the author of that? Who's sort of controlling it? Does it have a name? Where will we find it eventually? What's going on with that? Is it something that you'll try to actually turn into a product, or will it always be something that you're interested in just having available as a resource to people?
Yeah, the goal is to turn it into a publicly available web app at some point. That's the next step. We're currently wrapping up a grant through One Workplace, which is this next milestone for the beta version in Excel. But then the next step, I think, will be to take it to a publicly available web app. I'm not sure who will host it yet.
Mm-hmm.
Sounds
great. That was going to be my question too. I was very curious about the status of that. It's such a great tool. I can think of people out there right now who would love to use it. Some of them at DCAM, for example.
Yeah, there's a need for sure.
Yeah.
Speaking of the dearth of information, I know on the frontier of embodied carbon and studying the life cycle of MEP equipment is just in its nascent stages. So I really appreciate our architecture partners really leading the charge and kind of setting the standards here with regard to ways to think about this, tools to analyze it, because I think we engineers are going to be trying to keep up with you to look at these interventions in the same way. I think it's pretty common for a mechanical system is more likely to probably fail sooner than a building envelope potentially system, but to Elaine's point about there are these moments of intervention where you need to do something, you can really make an impact. I think we look at that kind of similarly on the engineering and on the operational carbon side. Well, I want to give everyone a chance to ask their questions here, but we certainly can wrap up a bit early. So Lori or Elaine, if you have any final thoughts that you want to share with everyone.
There's another question, by the way.
Oh, great.
And it says simply, could you show again the LCA tools that already exist and talk about pluses and minuses of them? That's a great question.
Yeah.
And for everyone, this is being recorded. So if you want to go back and study, there's a few things I kind of wanted to check along this line. But let's take a look at that. I think that would be great. I certainly was interested in Tally.
Sure. Yeah, so the tools, so Tally is the one we use. It's a plugin to Revit developed by Kieran Timberlake with Autodesk, and it evaluates the whole building. It takes the material quantities from your Revit model, and it has a proprietary database, which it was developed by Sphera, formerly Gabby. So Tally is really, the pluses of Tally are that it integrates to Revit and reads your material quantities pretty easily, and the user interface is very good. So if you work in Revit, it's fairly simple to use Tally. Although you do you know, with any of these, I'll say again, it's like energy modeling or any analysis tool where you kind of need to develop a little bit of an intuition to make sure you're checking the results, but that's, you know, for any tool. I would say one of the biggest downside for me of Tally is that because it has that proprietary database built in, it's not very flexible. So if you find a new product that you like and you have an EPD for it, you have to look at that manually. You can't build that into your Tally model because the database is locked in. One-click LCA is similarly a whole building tool, has more flexibility. I think it's a little bit more powerful. It's a European tool, so the database is it's not proprietary, but it's more European focused, but they also input materials that have EPDs. So if you find a material and you're interested in seeing it, they can actually pull it into their database. So you have more capability, and it can interface with Revit, or it can interface with you can use an Excel spreadsheet to enter your materials manually. So it's a little bit more flexible, but a little bit more complicated to use and more expensive. The Athena, I'm actually, this is not the name, the Athena Sustainable Material Institute is the organization, and I'm blanking, the Impact Estimator, that's the name of the tool. It's kind of higher level. It has, it doesn't read from a Revit model or anything. You kind of use, it takes you through a series of menu boxes to input your quantities and some assumptions about typology and everything. So it's not quite as accurate, but it's good if you want like a general sense. EC3 is the new embodied carbon and construction calculator, which debuted, when was that, like a year, right before COVID, it feels like forever ago, a year and a half ago at Greenbuilt. And that is basically a giant compendium of EPDs. So environmental product declarations, any product that has an environmental product declaration published basically is in EC3 or can be brought in. And what's nice about EC3 is that it has benchmarks and baselines and sets targets. So you can use it to, you know, for example, write a spec and say, I know that in carpet, the industry can support my setting a target of this global warming potential. So it's good for product selection and specifications, and it's good for procurement. EDGE is developed by the World Bank, which is really, I think it's more targeted towards developers in developing countries, but it's a really interesting tool because it's tied to more the financial aspect of it, but it kind of lets you play around with different inputs and understand, if I use this type of concrete or that type of concrete, what's my carbon impact? That's a free tool, a free web app tool. Those are the tools. And then the data is all, I don't know, I feel like the data is a little bit more boring, but you know, EPDs are from manufacturers. They have, it's like a nutrition label, but they're kind of difficult to use because they're not that consistent in the way they're produced. Some of these are public, federal LCA Commons and Circular Ecology's ICE database are public and free. Sphera by Gabby is a paid database, but these are all good if you just want to look up the global warming potential of a specific material.
And you can sort of mix and match these a little bit. So as Lori said, the materials available in Tally aren't comprehensive, but you can use the Excel file that it outputs as part of the results to then use, you know, data from EPDs to plug in, you know, more unusual materials that you're interested in testing out for comparison's sake.
That's great. Thank you very much. Sam has a comment and a question. The City of Boston, in its carbon reduction plan, calls for deep retrofits to existing buildings, yet most buildings are houses. I fear this would tend to disfigure old houses. Do you have any thoughts on that?
Interesting question, Sarah. Hi, Sarah.
Oh, I'm sorry, I said Sam. Sarah, feel free to unmute yourself if I didn't do justice to your question.
For what it's worth, you know, a deep energy retrofit, like Lori defined it, of on the order of a 50% energy reduction, I don't think needs to disfigure your house. I think that the bar to step over is quite low in the housing stock, especially the older houses, by sealing the cracks, insulating, you know, in between studs, replacing windows perhaps, all of those, need not have an impact from your building systems. Switching to maybe a heat pump instead of a gas-fired, or some older homes with a fuel oil heater. I think it's definitely feasible to have a deep energy retrofit within an existing residential structure, but the getting to net zero with one might be more challenging. But I think, Lori, to your point on the second case study, at some point, and I don't think the city of Boston's planning to use embodied carbon in their analysis, but at some point, keeping the existing structure and reducing the energy consumption within it is entirely feasible with it, and is likely a better path than significantly altering the structure, right?
Yeah, and I'm not as familiar with the residential regulations. I guess I'm more familiar with the large building regulations, but I think that you could make the reductions you need, as Patrick says, by air sealing and switching and fuel switching, by going to an electric heat pump. I don't think it requires disfigurement, but I think that this is part of an education and advocacy campaign of helping people to understand that something doesn't need to look overclad, or it doesn't need to be disfigured to be high performance. So that maybe is maybe more of a challenge in public perception and education than it is a technical challenge.
Yeah, I'll also note that the legislation that Boston is enacting is focused on larger buildings than houses. So, I'm interested to see what the future holds for targeting energy efficiency in residential structures, but the new legislation, I think, is at a higher level. And there's somebody that put a link in the chat for some examples of residential deep energy retrofits.
Lori, I really liked what you and Elaine were talking about a different sort of scale of this decision making around carbon and reuse of existing buildings, because it really is at a policy level, or at a planning or zoning level maybe, and then or with a large organization like DCAM, or all the way down to the level of staying away from spray foam insulation, or using wood structure instead of steel and concrete structure. So it's just, I think, really important to see that there's the ability to affect significant impact at a lot of different scales.
Yeah, thanks, Sarah. I think it's, I don't know. I think as we all become more facile in talking about embodied carbon and impacts in different ways, it's easier to work in a different scale, similar to the way we think about energy efficiency, from like turning on and off a light to carbon neutrality planning. Elaine, did you want to chime in?
Oh yeah, I mean, I was just thinking that I like zooming in and out and looking at this sort of discretely and at a larger scale, because I think it sometimes confirms, what we already know, which is that, some of our inclinations about interventions that we may want to make because they feel like they will introduce significant improvements, they're not really worth it, from an environmental perspective, even if there may be some like very minor energy improvement. So it's very educational to look at it through these different lenses, and I think it can help us make, just smarter decisions. The idea of overcladding is, sometimes appealing, for instance, when you're not talking about disfigurement, but that doesn't mean it's actually a good idea.
Yeah, appealing or frightening. And like the question about the houses, there are projects involving larger buildings that have really energy inefficient shells that real treasures, and there's quite a few of these in Boston. And it can be very scary to the people who are responsible for those buildings because they think, well, gosh, the main thing that's going to happen if I try to improve this is people are going to want to, you know, overclad this or do something that's going to destroy the appearance of it. And I think that you're showing that a data-based analysis done carefully can actually be counterintuitive and can show you some things that maybe you didn't expect and maybe allay some of your fears about what it's going to take to bring an older energy inefficient building up to current target standards or somewhere close to them. I actually thought it was really exciting to see what the real data might show and how that can be counterintuitive. And I hope that architects and other building professionals become better and better at providing owners with this, you know, data-based analysis that you've shown us.
Thanks, Michael.
I think it's still a little bit rare. I don't know that everyone has the ability to make it as clear as you guys have.
Yeah. Well, we were lucky to have this project whose focus was really to dive deep into this question. So. Elaine, were you about to chime in?
Oh no, I was just gonna say it's a work in progress, and I think it's really fun to be able to share it because it's something, you know, that we all want to be doing more of. So, and I think we can sort of build on each other's, you know, methods of representing the quantitative information to clients.
Don't see any new questions. I have a quick one, and it may be not even a great question. I'm not sure, but so let's say we get to 2015, we've made the grid 80% green. What does that mean for architects and building owners? What is that kind of preference and not? So some of us, like me, have been involved in really intensive efforts to make net zero buildings. You know, is our focus going to shift? Should it already be shifting? You know, what's the implication?
Wayne, do you want to answer?
Well, what I was gonna say immediately was I always think of it as a both and, because it's not as if the grid is ever going to get so green that more efficient buildings are not going to be helpful, right? And I guess this is it's reminding me a little bit of what's going on in part of the country right now, but it just feels as if it's, you know, all of these things can be, you know, rowing in the same direction, and it's incumbent upon architects and practitioners working on individual projects to help, you know, minimize the load of individual buildings to ease the strain on the grid. I don't know, Lori, were you going to say something besides that?
No, I think that's a great answer. It's good. Yeah.
Thanks. Okay, well, you're getting high praise in the chat, but I think we've wound through all the questions. Remember that this will be recorded, so for you attendees who want to go back and look at any of the details, that's going to be available. And I'll make a final plug also. Any of you who are interested or may know people who are interested in stepping up to the position of co-chair for the BSA Committee on the Environment, take a look in the chat near the beginning and submit your statement of interest to Susan Green at the BSA. And thanks everyone for coming, and thank you to our speakers.
Yes, thank you very much, Lori and Elaine. This is a fantastic presentation, really timely topic, and you really kind of elevated the conversation, I think, that we're having on the topic. And just a reminder, anyone, if you haven't filled out the form for your continuing education, go to the chat before we shut down the link and fill out the form.
Thank you so much. Thanks, everyone.
Thank you.
Thank you.
Thank you.